All right. FOSS1, limit of a sequence. I mean, this one you should definitely have, right? Give me the definition of the limit of a sequence.
For all epsilon greater than 0, there exists a big N such that if little n is greater than big N, the absolute value of an minus L is less than epsilon.
All right, you said that slightly faster than I wrote, but did I capture it? No, don't apologize. You said it at a natural pace. I was just asking you to double check. Yeah, I think that looks good. People happy? All right, limit point of a set. What does it mean to be a limit point of a set? Let's say it informally. So the informal definition of a limit point is no matter how close you look to this point,
For all delta greater than 0, there exists some x in U such that the absolute, or say such that 0 is less than the absolute value of x minus p, which is less than delta.
cool. Folks get that or something equivalent to? Yeah. So no matter how close you look to this point, you'll always see things in the set. And in fact, those things will be different from the point. Limit points are important. Oh wait, I guess the next line is isolated point. What's it mean to be an isolated point? Yeah. Yeah, so how about let's just say P is not, a limit point. And you can like now unravel that into like some quantified statement, which would also be correct, but maybe there's the laziest thing to write. Should we also write the quantified statement? Okay. If we need it later, then we'll negate it. We say that the limit of a function is equal to L if well, let's remember informally. It's like no matter how close you want f of x to be to L, you can get f of x to be that close to L by making sure x is close enough to P. And that should make you think of this definition. So what does that definition say? That definition says no matter how close you want a sub n to be to L, you can get a sub n to be that close to L as long as little n is big enough. Yeah.
For all epsilon greater than 0 and delta greater than 0.
Sorry, say that again. For all epsilon bigger than 0?
And delta greater than 0.
And we're switching to an erasable pen.
Such that the absolute value of x minus p is less than delta, and then you're also going to have the absolute value of f of x minus L is less than epsilon.
I like that inequality, I like that inequality, I like the for all epsilon bigger than 0. Let's think about what the job of delta is. The job of delta is a lot like the big N in the definition of the limit of a sequence. Instead of the delta having the job of saying, I want to let little n be really big, it's I want to demand that x is really close to P. So the first thing is like, it's not universally quantified. It's existentially quantified. For all epsilon bigger than 0, there exists a delta bigger than 0. No, but such that instead of if little n is bigger than big N, there will be an if absolute value of x minus p is less than delta, then absolute value of f of x minus L is less than epsilon. And there's still one thing missing.
This is true for all x.
Oh, sure. Yeah, I guess that's important too. And there's still another thing missing.
X can equal P.
Yeah, I need to do something to eliminate x equals p. And maybe the easiest way is doing that. Well, you could put a u set minus p there. So far, so good? And finally, definition of continuity. And even if you didn't fill it in already, now that limit is filled in, do you think you could remember? Yeah, so maybe I'll pause for another couple seconds. Let people write something in this line if they haven't already. Yeah, so I guess if you really want the for all statements, then there's a for all little n and big N up here too. So bottom line, yeah, what's the definition of continuity? Well, I'll start you with this for free. If f is continuous at p, then no matter how close you want f of x to be to f of p, you can get f of x to be that close to f of p, as long as x is pretty close to p. So, what should go between those two things?
The exact same stuff as in the definition.
Mostly. There exists a delta bigger than 0, such that for all x in U, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. Where if you want to include the 0 is less than here, you still can, because all you'll be eliminating is x equals p, and f of x minus f of x is less than epsilon, so that's fine. All right. With that little refresher, now I'm going to ask for honesty. How many people correctly have the definition of the limit of a sequence? Good. Definition of a limit point. Okay. Isolated point.
I need to check with the worded definition.
Oh, with quantified?
Yeah.
Oh, let's hear it.
I said there exists a delta greater than 0 such that for all u, or I use u, x.
We can use you.
Okay, I use u. For all u and u, if the absolute value of p minus u is less than delta, then p is in big U.
P is equal to U. Which would mean that P is in big U, but that specifically. Cool. How about definition of the limit of a function? How many people have that? All right. Definition of continuity. Cool. So some things will be on a pop quiz, which hopefully I will ask again on Monday. Because today's Friday. Yeah.
For isolated point, can you also say such that u minus the absolute value of u minus p is greater than or equal to delta or x equals p?
Yeah, that's cool.
Something like that.
Groovy. So, there are relationships between these things. And this is what today is all about. Today is all about how can you detect all of these new complicated function-y definitions using only sequences, which we have lots and lots of tools for. And maybe before that, let's remember that continuity and limits are related. So here's one result we proved. F is continuous at a point if and only if the limit as x approaches p of f of x is equal to f of p. What were the assumptions we needed on that theorem? Flip back if you need. It's a limit point. If p is a limit point of u, then continuity detects limits. There was another proposition we gave that for a different flavor of point, just functions are continuous, it doesn't matter. What type of point was that? And again, if any of you were like laptop users who were like wielding the PDF instead, that's hyperlinked, clicked. But you're not, so you can't. Say again? Nope. Isolated point. Whenever you're at a point that's not a limit point of the domain and is in the domain, then everything is continuous all the time, no matter what. And basically the proof was, well, to check for continuity, you need to check at inputs that are nearby. There are no inputs nearby to check, so there's nothing to check. Today's main theorems are going to be the following. Limit points of sets, limits of functions, and continuity of functions can all be detected in terms of sequences. Here's the first. Sequential reformulation of a limit point. Let u be a subset of R, and p be a point in R. Then p is a limit point of u, if and only if there exists a sequence, xn, such that for every natural number n, xn is in u and is not equal to p, and xn converges to p. And maybe we'll like draw a picture of the proof. We'll do like a formal proof in a little bit, but let's try to convince ourselves of that. So the intuitive idea of a limit point is that if there is p, then as long as I look close to p, and no matter how close to p I look, if there's p plus delta and p minus delta, I should always be able to find things in the set that are within that neighborhood. So let's take that little delta neighborhood. And let's suppose we have the sequence xn that converges to p. Let's draw a picture of that sequence. Maybe it starts out far away. Maybe it escapes a little bit. But it converges to p. Eventually, is that xn in that interval? So I don't know, maybe there's like x sub 25. So that x sub 25 is in between p minus delta and p plus delta. Is it different from p? Yeah, by assumption. Oh, does that, like, give you something that satisfies that inequality automatically? Cool. So sequences detect limit points. That's not a proof, but I think it's convincing anyway. Sequences also detect continuity and limits of functions. Sequential continuity. And we'll use this theorem an awful lot as the semester progresses because it'll let us say, this theorem about functions is too hard to prove. Instead, I'll use that I've already proved something about sequences. So here's the theorem. Let u be a subset of R, f be a function defined on u, and p be in u. Then f, that doesn't really need to be an x there, is continuous at p, if and only if, for every sequence xn of elements of u which converge to p, it follows that f of xn converges to f of p. And that's like a lot of words, but I think it'll help to draw a picture. Or maybe just give the intuitive argument. Continuity means something, right? And here's like the intuitive definition. F being continuous at p means when x is close to p, f of x is close to f of p. Right, that's all continuity means. Like the precise definition is one interpretation of it. And now let's try to put that together. If xn converges to p, does that mean xn gets close to p? Xn converges to p means xn gets close to p. Oh wait, but if xn is close to p, then what can you tell me about f of xn? Cool. Oh, but that's like exactly what it should mean for f of xn to converge to f of p. So that's like clearly not a proof. I guess for certain it's only one implication instead of like the felt if and only if. But hopefully that like is convincing that it's probably true. Do you think you could write something similar for this limity statement? Let u be a subset of R, f from u to R be a function, p be a limit point of u, and L be a real number. Then the limit is x approaches p of f of x is L, if and only if for every sequence of elements of u minus p, such that xn converges to p, then f of x converges to L. And maybe I'll just say the laws this time. Limit of f of x is equal to L means when x is close to p, f of x is close to L. Does the sequence xn get close to p? Oh, cool. So that should mean f of xn gets close to L. There's another convincing thing. Before we try to prove these, which we'll prove the first two of these theorems. That is the one on the previous page in 7.2.2. Do you think the proof of those two is probably going to be pretty similar to each other? The proof of this is relegated to a challenge problem / extra credit. So if you pay close attention to the proof for continuity, I bet you can do that one free of charge. Or, easily enough. Before that, though, let's apply these to these algebraic limit laws that we didn't prove. Well, one of them you proved as like a homework. How many people have done that homework yet? The one where you prove a limit law for all functions. Okay, that's fair. It was assigned this most recent time. Let's write down these facts, and then we'll go through the proof of one of them. Assuming theorem 7.2.3. If f is a constant function, then what should the limit as x approaches p of f of x be?
C.
If f is the identity function, then same question.
X.
Yeah, x is getting close to p, so like p is where the limit is being taken. If f of x gets close to L and g of x gets close to m, then what does f of x plus g of x get close to? The sum? Same assumptions, but you do subtraction. Get the same conclusion. Multiplication also works. And division, as long as you don't accidentally divide by 0. Seem all right? Let's prove one of those by appealing to theorem 7.2.3, which is at the top of the page, along with limit laws for sequences. So let's go ahead and do it. So we're going to prove the claim about division. All the rest of the proofs will be the same. So imagine how you would change this to get a different one of the claims. So let's start with the setup. Let's let U be a subset of R. Let's let P be a limit point of U. Let's let F and G be functions. There's no assumption about continuity. That's a mistake. Let's assume that the limit as x approaches P of F of x is L. Limit as x approaches P of G of x is M. Let's assume that G of x is not equal to 0 for absolutely any x in U. And let's also assume that the limit of g of x is not equal to 0. We need to prove that this limit is equal to L plus L divided by M. And our proof is going to pass through this theorem at the top of the page. And maybe I'll rewrite the statement on the board because it doesn't fit on the page. So there's what I want to prove. Theorem 7.2.3 lets me translate that to something else. Instead of proving this, I could prove for every sequence xn of elements of u minus singleton p, f of xn over g of xn, there's an important assumption I left out. If xn converges to p, then is that a correct application of 7.2.3? Yeah, for this particular function. So I'm going to use this. I know what I want to prove. I want to prove that for every sequence of elements of u minus p, so let's let xn be any sequence of elements of u minus p, if xn converges to p, so let us assume that xn converges to p, here's what I want to prove. I'm going to also use that this is an if and only if. I know that f of x converges to, I know the limit of f of x as x approaches p is L, right? So, by theorem 7.2.3, what can you tell me about the limit as n goes to infinity of f of x sub n? What do I know about f of x?
Converges to P. Oh, sorry. I was answering my own question.
As x converges to p, f of x converges to L. So this xn converges to p. So f of xn must converge to L. Same thing for g. What can you tell me about the limit as n goes to infinity of g of xn? Do I have a division limit law for sequences? Nice. And the assumption in that division limit law is that you never divide by 0. Do I have something here that'll prevent division by 0? Yeah, I know g of x is never 0. So what can you tell me about the limit as n goes to infinity of f of x sub n divided by g of x sub n? All right. So let's see. Have we now proven that for absolutely every sequence xn of elements of u minus p, that f of xn divided by g of xn converges to L over n? This is an if and only if, so I get the conclusion I want. That's going to happen on the next page now. Thus, we see that from absolutely every sequence, I like my sequences to have parentheses around them today, of elements of u minus p, which satisfy that xn converges to p, we have that it follows that the limit of f of xn divided by g of xn is equal to L over m. Thus, by theorem 7.2.3, I conclude this. So notice, I used both directions of the theorem. I translated the assumptions about f and g to things about sequences. And then at the end, when I had something about a sequence, I translated it back to something about a limit of a function. So it's really important. It's useful to have an absolute reformulation of stuff. Oh, yeah, you want to actually see what's going on. Yeah, that's fair. Groovy. So, hopefully you're convinced that these three theorems are like useful in that we know lots of things about sequences. And if you want to prove anything about limit points of sets, or limits of functions, or continuity, you can probably translate to something about sequences. Say, well, I've already proven it for sequences, and then translate back. So these are like powerful theorems. I think we should prove them. And let's start with the proof of 7.2.1. And you know what? The statement of 7.2.1 was a while ago. I'm going to put it on the board, which means I'm going to flip back to the previous page. You don't have to if you don't want to. 7.2.1, the sequential reformulation of limit points, says let U be a subset of R and P be in R. P is a limit point. I'm going to use that abbreviation a lot because limit point is too many things to write. And I don't think there are too many other things that are also abbreviated LP right now. So I think limit point is, or LP is okay. P is a limit point for U, if and only if there exists a sequence xn of elements of U minus P with xn converging to P. So let's try to prove that. And the proof will even be like pretty quick, I think. So it's an if and only if. So there will be two implications to do. Let's start with one of them. Let us assume that P is a limit point of U. Let's remember the definition. What's it mean to be a limit point? By flipping back or just from memory. I think some people had it from memory before.
For all delta greater than 0, there exists x in whatever set we're dealing with U, such that absolute value 0 is less than the absolute value of
Oh, sorry. Oh.
x. Yeah. X minus whatever we're calling the limit point.
P. Cool. I'm going to make the following. That's correct. I'm going to make the following change, and it'll give the exact same statement, but I think it'll look more like what I want. Is that the same statement again? Yeah. You just need something to eliminate x equals P, and here I see something about U minus singleton P. So let's write it that way. I need to find a sequence of elements of U minus singleton P such that xn converges to P. Is that a pretty good statement of the want to show for this direction of the proof? If I want to show there exists such a sequence, then I guess one way to prove that something exists is by finding it. Not the only way, but that's a good way. So, let's see, I want to construct a sequence worth of elements of u minus p. For each delta, I get an element of u minus p. Let's start with a sequence worth of deltas. So, for absolutely any natural number n, I'll pick my favorite sequence that converges to 0 and is positive. Let's let delta n be 1 over n. Does that delta n satisfy everything I need this delta to satisfy? So I can appeal to this. So since p is a limit point of u, we see there exists some element of, by the way I wrote that, this is a u minus singleton p, such that absolute value of xn minus p is less than delta n. So let's see if this notation even makes sense. Different choices of delta result in different choices of x. So x depends on delta. But each choice of n results in a different choice of delta. So this x really does depend on which n I choose. So it is a sequence worth of things. All right, good. Do I now have a sequence worth of elements of u minus p? What do I want to show about the sequence? How about that? I want a sequence that converges to p. Let's try to show that this sequence converges to p. So I need the sequence to converge to p, and I guess I also need it to be in u minus singleton p. So far, so good? All right. Well, I think now it's like it's going to be pretty automatic, right? I want to prove that this sequence converges to p. So I know how to prove a sequence converges. Let's consider any epsilon bigger than 0. We'll come up with a choice of big N. We'll consider any little n bigger than big N. Well, what do I know about the absolute value of xn minus p? I know that it's less than delta n, which is 1 over n. So I just need to show that 1 over n is like really small. And I think you even know what I'm going to do next. Little n is bigger than big N. So what can you tell me about 1 over little n?
Less than 1 over big N.
That seems useful. And I'd like this to be equal to epsilon. Is there a choice of big N that will result in that being equal to epsilon? I guess if you need to go after like the margins and I guess solve that for big N. So I guess I better put that like up here. Oh, does that look like a complete proof that the sequence converges to P? Groovy. So the limit of the sequence is P. What do I still need? I still need that for every natural number n, xn is in u minus p. Do I already have that? Well, let's go ahead and scroll on up. Let's look at where we constructed the sequence. Since P is a limit point of view, we see there exists some sequence of elements of u minus P. Oh wait, do I just already know that every xn is in u minus P? By our very choice of xn, we see that xn is in u minus singleton P. Does that do the job? Does that build the sequence I needed to? Yeah. And I think if this were like the type of proof you would see in like most research papers, it would probably stop about there. And then say, oh yeah, it's now obvious. Because hopefully that stuff down there did feel pretty obvious. Let's flip to the next. So, well, it says this completes the proof. Does that complete the proof of the whole of the theorem? It completes the proof of half of the theorem. So maybe that parenthetical is worthwhile. I wouldn't say it's important. But. So, other direction. Let's assume there exists a sequence, xn, of elements of u minus p, which satisfy that xn converges to p. I need to prove that p is a limit point. So we assume there exists a sequence of elements, xn, so that for every natural number n, xn is in u minus singleton p, and which converges to p. I need to show that p is a limit point of u. And I know, like, I literally asked this like 2 minutes ago, and it's on the previous page. What's a limit point? To show p is a limit point, I need to show that.
Such that 0 is less than the absolute value of x minus p, which is less than delta.
Awesome. All right, so let's try to do exactly that. There's a statement I need to prove. So I better start by saying consider any delta bigger than 0. Now I need to come up with the right choice of an element of the set big U. The only thing I have right now is the sequence, so I think I need to use the sequence to guide it. Delta is bigger than 0, and the sequence converges to p, so what does that tell me? Eventually, xn minus p is less than that delta. I could do that for any positive number. Delta is the only positive number I see. If I like start going through the proof and find out that I'd like this delta divided by 2, then I'll divide it by 2. Maybe I'll even color code it so I can tell where the deltas are in case I do need to divide it by 2. I don't think I'll need to, but better safe than sorry. The definition of the limit tells us that there exists a big N such that for a little n bigger than big N, absolute value xn minus p is less than delta. And that delta could be any positive number I want, but since like this looks a lot like that, I think that's what I don't want to do. I think delta is what I want. You can divide it by 2 if you want to divide it by 2. You can always make your delta a little smaller. All right, so let's do the job. Let's consider any little n bigger than big N and see if we get what we want. That little n bigger than big N, then what do we want? This isn't part of the proof. This is like, well, then it should be off to the side. We want xn in u minus singleton p, and I want absolute value of xn minus p less than delta. So tell me, why should those things happen? Let's start with this. Does this happen all right? Nice. So maybe we'll label this with like a little star by star, since little n is bigger than big N, absolute value xn minus, oh no, god damn it. There's the one to show we want the 0 is less than portion. But we still get this much automatically. All right. So now, tell me why absolute value of xn minus p should be bigger than 0. What's the only bad thing that can happen? Yeah.
I was going to say xn cannot be that's my assumption.
Cool. Which assumption?
Xn exists in u without p.
Yeah, that seems pretty convincing. So, 0 is less than the absolute value of xn minus p. And let's just see if we've done what we wanted. We want to show FOE delta bigger than 0. We considered an arbitrary delta bigger than 0. Question?
We also have to show that xn can't equal 0.
Xn equals 0 would be fine. I just need, well, I need xn minus p to be bigger than 0. I have absolute value of xn minus p bigger than 0. Xn could be equal to 0, as long as p isn't equal to 0, yeah. So we've constructed an element xn in the place where we want it to be, such that, well, I guess here I wanted it to be in u. This is the trouble of there being like the couple of slightly different definitions of the same statement. If I try to pre-type everything, then I'm probably not following the right definition, but like they're all equivalent. So here's a limit point. Feel pretty good so far? Let's make as much progress as we can on the continuity statement. And instead of writing it down again, I think that I'll restate the assumptions right here. So proof is 7.2.2, let U be a subset of R, F be a function from U to R, and P be in U. These are the two statements we want to show are equivalent. Flip back to the previous page if you want to double check that I've done that correctly. But I think those two are the two sides of that if and only if. Let's try to prove it. So, yeah, maybe I'll flip back to that previous page because people seem to want it. 7.2.2. Let U be a subset of R, F be a function from U to R, and P be a point in U. Then F is continuous at this point P, if and only if for every sequence of elements of U, satisfying that xn converges to P, it follows that f of xn converges to f of P. Is that now in line with what's written there? Okay, that's good. So, let's try to prove that. So, we know how to prove something like that. Like, if you want to prove an if, then assume the if part. So let's assume that f is continuous at P. I want to prove something about every sequence of elements of U that satisfy that convergence condition. So let's assume that xn is a sequence of elements of U, and that xn converges to P. We need to show that f of xn converges to f of P. And we even know like how we would begin such a proof. If I want to prove something about a limit, I better start by considering any epsilon bigger than 0. And in order to come up with what's going to go in these coming lines, I'm going to appeal to the picture at the bottom of the page, which isn't like an incredible picture. It's just a picture of some function that's described continuity. So continuity says, let's maybe include what I want. Eventually I want f of xn to be really close to f of p. So I guess if there's my epsilon neighborhood. So there are things that are within a distance of epsilon of f of p. Eventually I want f of p to be in there. Continuity says that there is a choice of delta so that as soon as x is in that delta neighborhood, f of x is in that red neighborhood. Is xn eventually going to be within that little blue delta neighborhood? Yeah, because xn converges to p. Let's just put those ideas together in that order. So, consider any epsilon bigger than 0. First thing I did was continuity. So let's use continuity. Since f of x is continuous at p, there exists a delta bigger than 0 such that for all x in u, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. This delta is bigger than 0, and xn converges to p. That means that eventually xn is in that little blue delta neighborhood at the bottom of the page. But like, what's the formal statement of that? That statement is there exists a big N such that for all little n in the natural numbers, if little n is bigger than big N, then absolute value of xn minus p is less than delta. All right, so now let's just put those two things together. Let's consider any little n bigger than big N. Then by 7.2, absolute value of xn minus p is less than delta. Oh, but then by 7.1, you know what I'm about to write, right? I have the if part of the if then. So let's write the then part of the if then. Cool. That seemed like a proof of convergence of a sequence? Nice. And I've got 4 minutes left on the clock. Let's see what progress we can make in the reverse direction. And the reverse direction, I think the only complicated bit is going to be figuring out some like logic to guess the right statement to try to prove. So, reverse statement. So, the reverse statement is, well, is like exactly this, but without the knots and the arrow going in the opposite direction. Is like the other half of the if and only if that needs to be proven. So this is equivalent to that, right? By the principle of contraposition. Instead of proving if this, then that, you can prove that if not that, then not this. So let's try to prove if a function is not continuous, then the negation of that statement should hold. So I guess that means instead I need to show that there exists a sequence of elements of U that does some stuff. And let's go to the bottom and see if we can come up with one. Here's a function that is not continuous at this input P. And let's not worry about like the full statement. Can you see based on that a sequence worth of inputs that gets close to P for which f of that sequence does not get close to f of P? Yeah. It's that one. So like, it seems compelling that you should be able to do such a thing. And the actual like walk is going to be like going through the motions of figuring out the logic for the steps. So, I got 2 minutes, so let's at least make a start. I want to prove not continuity implies not that. So let's figure out what it is that we need to prove. What do you get when you negate this? There exists a sequence, xn, of elements of U, such that, because it's there exists. Yeah.
If xn approaches P, then f for xn is not approach f.
Not quite. So when you negate an if-then, you're saying that there exists a counterexample. So you need to prove that this sequence satisfies the if part of the if-then, but not the then part. So it's not an if-then anymore, it's an and not.
Such that xn converges to p and f of xn does not converge to
All right, so that's what we need to come up with. And let's see. Does the sequence at the bottom of the page seem to do that? Xn converges to P, f of xn does not converge to f of P? Nice. So there's what we want to show. Let's also negate the definition of continuity to see what we actually get to assume. Well, I don't know. Maybe at this point I am actually, I'm not going to finish because I'm at time now. So here's what I think I would like you to do between now and Monday, in addition to all the other shit that I ask you to do. Try to make a start on this. Like, at the very least, you can negate the definition of continuity to see what the assumption is you have. Go from there and try to go down. If we're even just like happy with this proof, then great, we won't need to talk much about it. And if you're in particular happy with this proof, then the start of class on Monday will feel super light. Okay, now I'm done. I'm going to quiet now.